Hello everyone, welcome to this presentation called Introduction to Linear Hyperbolic Conservation Laws. My name is Hugo and this is a two-lecture series presentation. In this first one, I will be focusing on talking about this kind of equations that are also important in computational fluid dynamics. In the second lecture series, I will be focused mostly on talking about finite volume methods for solving these equations. But in this presentation, I want to give a quick introduction to these hyperbolic conservation laws and why they are important, why their study is important. Then I will be focusing on talking about the simplest hyperbolic conservation law, which is the linear advection equation, and then we will solve this very basic example in order to obtain its analytical solution. Then I also want to discuss about discontinuous initial solutions in this kind of systems. Then I want to give a quick introduction to a very important concept in hyperbolic conservation laws, which are the characteristic curves. And then lastly, I want to talk about the boundary conditions that need to be imposed. So, hyperbolic conservation law. What is an hyperbolic equation? Hyperbolic partial differential equations appears in nature and also in different disciplines where wave motion or convective transport is important. So, convection or advection is that transport of a substance or a property due to the bulk movement of a fluid. So let's say, for instance, we have a fluid. It can be water, it can be the water in a river. So within the fluid, there might be some particles, some pollutants, some contaminants. So with these equations, we want to track the movement of these particles within the fluid as the fluid is moving. Some examples that appear in nature can be, for instance, the movement of particles with moving air. So, for instance, in the industry, you know that they have chimneys and they release pollutants. They release these huge plumes. So, they are releasing contaminants. So, with these equations, we can track these particles, these pollutants, as they are being released into the atmosphere. So another example can be pollutants downstream in a river. As I was saying, we might have a river, so there might be some particulate matter within there, and as the fluid is moving downstream, we want to track the concentration of particles in the river. Also the movement of bubbles rising to the surface of a lake. And these PDEs, these partial differential equations, are derived from conservation laws. And we know that any conservation law states that certain quantities, in this case, the concentration of a substance, these quantities are conserved. So that means that we cannot either create or destroy these substances. They are just being conserved. So now let's talk a bit about the mathematics of these equations. So let's consider we have a one-dimensional system. So a homogeneous first order system of PDEs in both position and time t has the form of equation 1. So this is a system of equations where we have a temporal derivative and here we have an advection, a convective term. So Q is a vector of m components representing the unknown quantities. So Q can be either, for instance, concentration if we are talking about particulate matter. It can be pressure if we are talking about gases. It can be also velocities when we are talking about fluid systems, etc. And then we have that Q is dependent on both position and time. So we have here changes, temporal changes of Q. And then in this term, we have a matrix A, which is a constant m times m real matrix. And then here we have the spatial changes of Q, because Q can also change with position. So this equation represents a system of PDEs. So for the case of, in this case, we are only considering the simplest case, but there might be another equations in which we have a source term. We might have here another term. So this kind of equations can describe, for instance, chemical reactions, where you might have here a source term, which can be, yeah, as I was saying, a chemical reaction. These equations also appear in shallow water equations, which are these kind of equations that are used to model flows in a river, tsunamis, etc. And yeah, this equation 1 represents a linear system of PDEs, but equation 2 is the equation that appears mostly in literature. So the temporal derivative is represented as Q t, and then this spatial derivative is represented as Qx. So yeah, remember that Q is a vector. So this equation, as I was saying, this equation represents an hyperbolic system, but in order to be hyperbolic, this matrix, this equation 3, has to satisfy certain conditions. And those conditions are that the matrix A has to have real eigenvalues and a complete set of linearly independent eigenvectors. So that's something important to mention. And the simplest case is the constant coefficient scalar problem, where m, which is this index that appears here, if m is equal to 1, a becomes simply a scalar value. So this equation 5 can be simplified to this equation 6. We no longer have a vector equation. So now we have a scalar equation, which is the simplest case of 1D conservation law. And here I introduce this function, which is called the flux function, which is just simply a function that is going to depend on this Q, which can be, for instance, if we are tracking the concentration of a particle in a river, so Q stands for the concentration of that particle. And we are interested in studying their temporal changes and their spatial changes. So these equations, conservation laws, typically arise naturally from physical laws in integral form, stating that for any points x1 and x2, we have this equation 7. So yeah, conservation laws, these equations come from conservation laws, and here I will give a quick example. So let's say we have this geometry, we have this rectangle that is it has this size. Here at the left border we have a coordinate x1, and the right border we have a coordinate x2. The length of this geometry is given by x2 minus x1, and then inside this geometry we have some fluid within. It can be water, it can be any kind of fluid you want to model, but most importantly, within the fluid there might be some Q quantity. So this Q quantity represents a property. So this property can be, in the case of gases, it can represent densities, it can represent in the case of gases it can represent pressure. In the case of multiple fluids, it can represent densities. In the case of particulate matter, it can represent concentration. But Q is just that property divided by a characteristic length. In this case, it will be this length here. But this is the 1D case. In the 2D case, we, instead of property over length, we might have property over an area, over a cross-section area. And in the 3D case, we will have some sort of density, which will be given by the property divided by a volume. But in the 1D case, it's property divided by length. So yeah, so Q, here this term in the left, we have this Q, that is the quantity that is within the fluid. And now remember, Q depends on X and T. And let's say you have multiple values of Q as X, as you vary X in X direction, which is from left to right. So you might have one value of Q at this coordinate. You can have another value of Q here, another one here, another one here. So when you take the integral over this domain, over x1 domain, you are obtaining the total quantity of Q. And you can see from the units, Q is a property divided by length, and now you multiply by this differential that has units of length. So the integral will give you the total quantity of the property inside this domain. In the case of particulate matter, the integral will give you the total mass of a particulate system, of a particle. But you are interested in the variation of Q with respect time, so you obtain the derivative with respect time of this quantity, of this integral. Yeah, because there might be something changing here, so you want to study how Q varies with time. So from typical conservation law, these changes of the property can be due to something is happening in the system that is going to change. It's going to affect this temporal variation of Q. And in the case of hyperbolic conservation laws, these densities, these changes in Q can be due to a flux difference. So flux, you remember, is a flow of a property divided by an area, by a cross-section area. So at this border, something is entering here. There is a flux crossing this border. So this flux is evaluated at x1, which is this quantity. And then there is another flux. Instead of entering the system, it's leaving the system. So as you can see, Q will only vary with time if there is some non-zero difference between these two fluxes. So these fluxes are the inflow, that means the quantity of Q that is entering here, minus the outflow at x2. That means the quantity of Q that is leaving the system. So yeah, this equation states that the total quantity of Q between any 2 points can change only due to the flux past the endpoints. So this is the basic idea of where these equations come from. So some example of an hyperbolic system is the single phase flow in porous media. So porous media, it can be, for instance, the flow of a fluid through a sponge or through a rock. This kind of single phase flow in porous media is very important in oil extraction, because the industries extract the petroleum from the ground, and the rocks are porous, so they need to model how the petroleum flows through those porous rocks. And this flow in porous media is given by these equations 8 and 9. So we have the porosity when this phi value is the porosity. When the porosity is equal to 1, that means that all the fluid will go through the sponge or through the rock. And when phi is smaller than 1, That means that the fluid will have some porosity, so there might be some fluid that will not flow so easily. And then C is the concentration of a substance. We have here the fluid velocity, the partial variation of the concentration, and that has to be equal to 0. This equation is valid in a domain, in a given geometry. So in order to solve equation 8, you have to satisfy one initial condition. That means that at time equal to 0, you will have a concentration profile in the whole domain. And when you have your boundary condition, which means that the concentration at one of the borders has to be equal to a profile in the borders of the domain. CB is the concentration at the entry borders. So this is just one example of a very important equation that is an hyperbolic conservation law that is used in the industry. So in this case, in this talk, we will focus for simplicity in the linear advection equation. So this equation is used to model, to track a substance being carried along with fluid motion. So for instance, a contaminant being advected downstream with some fluid flowing, for instance, through a one-dimensional pipe or one-dimensional channel. So this equation 10 represents the linear advection equation, which is the equation we already showed before. But here I'm introducing this flux function. So this flux function is equal to a fluid velocity, which is given by u bar. So the fluid is going to move, the fluid that carries the particulate matter will have a velocity u bar. And then the flux function is given by the product between this fluid velocity that is constant multiplied by the derivative of q with respect x. So we have equation 10. And now let's quickly solve this equation. It's very easy, so we just need to impose, for simplicity, this special domain. So that means that we will have an infinitely long channel. This is the domain, and then we will impose some initial condition. So that means that the concentration profile of Q at time equal to 0 is going to be a profile that we will specify later. But where x is element of the real numbers. So how do we solve this PDE? So it's actually very simple. So we will use this strategy where we assume a parameterization for the variables x and time of this form. So x will be dependent on this theta parameter, and then t will also depend on this parameter. So if we do this parameterization, q will be this equation 12. So q dependent on x, and t will now be q dependent on x that depends on this parameter, and that q also is going to depend on t and t depends on this parameter. So if we use rule change, so that means we will obtain the derivative of q with respect to this parameter. We apply the rule change, we obtain these relations, and then we end up with this equation 13, the right hand side. So you can notice that from this right hand side, this equation becomes equation 11, the equation that we have here, under these conditions. So here it should be dx with respect this parameter. So you can notice that qx multiplied by u becomes this term under this condition, and this equation, this term, in order to be equal to this term, has to be the derivative of t with respect to this parameter has to be equal to 1. So under these equations, under these conditions, the conditions from equation 14, equation 13 becomes equation 11. And thus, we have the following equation. So the dependence, well, the derivative of q with respect to this parameter is equal to this equation, and we know that from the equation 11, this equation is equal to 0. So what is the meaning of this? It means that the solution q will not depend on this parameter. And knowing that, we can now solve the ODEs, the ones from equation 14. Yeah, we solve these equations for x and t, and which can be easily solved. You just need to consider the initial conditions. We know, for instance, that from here, this is the easiest one. So yeah, you solve this equation, you end up with this. But at t0, remember that when you solve an ODE, you will get a constant, and then you need to evaluate that constant that is t0. But we consider that the initial time of our PDE is 0. So this equation tells us that t is actually just this parameter theta. We do something similar for the this equation. We solve the PDE, we obtain a constant that has to be evaluated. So that constant is going to be equal to x0 plus a parameter, the parameter evaluated, the parameter multiplied by the fluid velocity. So yeah, we have equation 17, but remember from equation 15, we know that q does not depend on theta. So now for simplicity, let's take that this parameter theta is going to be equal to 0. So this equation q dependent on x and t is going to be now only q dependent on x0, because if we set theta equal to 0, this term with the u bar multiplied by theta is 0, and then this term is also going to be 0. So yeah, we have this equation, and from this relation, and recalling that t, from equation 16, t is equal to theta, we can deduce the following. So once again, we obtain this equation here that appears here. So q x0 evaluated at time equal to 0 is just q evaluated at x0, and then from here, from equation 16, we have we isolate x0 from this equation, and we obtain this this term x minus u bar multiplied by theta. But from here, also from equation 16, we saw that theta is equal to t. So we obtain this right hand side of equation 18, and that's our solution. So what does this equation tell us? So this equation tells us that the solution qxt is just the initial condition. Remember, we impose at the very beginning an initial condition of this form. So we impose a profile q at time equal to 0. This profile is going to depend on x, but the solution is just the same profile q0 that we impose here, but now instead of being evaluated at x, it's going to be evaluated at x minus u bar multiplied by t. So this means that the solution is just the initial condition displaced by this distance ut. You can see that from the units from this term is velocity has units of distance over time, and then if you multiply distance over time by a time, you have units of distance. So yeah, we have something distance minus something that has units of distance. So in other words, the solution of an hyperbolic linear problem, is just the propagation of a wave set by the initial condition with velocity u. So this is just some those are some words, but now let's see this in a graph. So let's put some values to these parameters. So we assume that the velocity, the fluid velocity, is going to be equal to 1, and then we will impose an initial condition of this form. This is a Gaussian form, a Gaussian equation that is going to be centered at x equal to 1. So yeah, and we impose this profile and this value into this solution, we end up with something like this. So here we are plotting the profile Q, and then here in the x coordinate we have the values of x, which is the position. So at time equal to 0, which is this blue curve, we have the initial profile, which is this one. So from here you can see that when x is equal to 1, 1 minus 1 is equal to 0, but the exponential of 0 is equal to 1. So yeah, this Gaussian is centered at x equal to 1. And what happens when you increase the time? Well, you can see that you obtain this orange curve, but you can see that this equation, this function, the shape of this function remains the same compared to the function or the profile at t equal to 0. But this orange curve that is being evaluated at t equal to 2 is now, it was displaced now this distance, because it's going to be this function is being displaced from left to right. You can see this also the same behavior when we increase the time to t equal to 4. Now the wave appears here. It's being displaced more and more to the right. Yeah, you can see also the case for t equal to 6. So yeah, so the solution of the system is just the initial condition, this one, being displaced by this distance. And also the solution of this problem here is just a wave here that is being propagated with velocity u. So yeah, this is just the physical meaning of this solution that we obtained in equation 19. So now I want to mention quickly something important. It is very important to mention that the initial conditions of the hyperbolic problems, like the ones that we impose here, the velocity, the profile Q0. So this kind of hyperbolic conservation laws allow to use discontinuities, which can be propagated without any alteration. So here I include some example. So yeah, here we are imposing an initial profile for Q, where equation 20 says that if, yeah, here we have the x coordinate. If x is smaller or equal to 0, the value of Q is going to be equal to 1. But if x is greater than 0, we have a value of Q equal to 0. But now, if we apply this initial condition into this solution, you can see that this discontinuity is also being propagated from left to right. So at time equal to 1, now this discontinuity will appear here. And now when time is equal to 2, now the discontinuity appears here. So once again, yeah, the solution of this, the initial profile imposed at the initial time is being displaced from left to right. So these discontinuities are important for solving problems that are relevant. For instance, in gas dynamics, also when you have multi-phase flows, where you can have multiple fluids with different densities. So there is going to be some discontinuities in the densities. You can also encounter these discontinuities in dams, in the flows of a river. For instance, you have a river that that is coming from a mountain that has at the left the river is coming from a very high height, and down, and now it will fall to reach a lower level. So you will have a difference in heights for those waterfalls or those rivers. Yeah, and also these discontinuities can also appear in tsunamis. Yeah, so these discontinuities appear. They are very common in geophysical flows. Another important thing is that one disadvantage of the finite difference method, because we can use we can try to use the finite difference method to solve this equation, because this equation is very simple. It's a linear equation. But the disadvantage of the finite difference method is that those methods, the accuracy of those methods rely heavily on the local derivatives in the problem, because you know that in order to evaluate the derivatives in the finite difference method, you need to apply Taylor series, and also the Taylor series have to be evaluated in a close point, in a point of interest. Also, we have to assume that the functions are going to be smooth. So for those reasons, we cannot use finite difference method, because yeah, when using discontinuities in the equation, the finite difference method cannot treat those discontinuities, because the finite difference method requires continuity in the functions. So yeah, the finite difference method is not a candidate to solve hyperbolic conservation laws using discontinuities. So this is just something I wanted to mention, something remarkable. So now I also want to talk about characteristic curves, because these curves help us to understand the behavior of physical PDEs in more detail. But what are those characteristic curves? So these characteristics are paths in the position and time plane. So these paths are going to be denoted by this sigma, and this sigma is going to depend on this capital X, dependent on t, and yeah, the sigma are also going to be dependent on time. And under these paths, the solution is constant. So how do we obtain these characteristic curves? So remember, from this is our linear advection equation, which is a scalar equation. So if we obtain this derivative, which is the derivative of q evaluated at this capital X, we will be talking about this capital X in a moment, but yeah, let's evaluate the derivative of q there with respect time. So you obtain this relation. So you have qt evaluated at capital X and evaluated at time, plus you have qx evaluated at capital X and time, multiplied by the derivative of capital X with respect time. And this equation is equal to 0. And once again, you can notice that equation 21, the right hand side, can be similar or is similar to the linear advection equation. But this is only true, this right hand side of equation 21 is equal to this equation only if this derivative of x is equal to the fluid velocity. So solving this ordinary differential equation, you obtain this equation. Capital X is just capital X evaluated at time equal to 0 plus this distance, which is given by the fluid velocity multiplied by time. So now let's make some plots. Here in the literature, it is common to see this kind of curves where you have t time, and here the coordinate t is the vertical one, and the coordinate x is the horizontal coordinate. So these paths, these characteristics, these straight lines that we obtain from this equation are these ones. So if you plot t versus x using these straight lines, you obtain these curves. So the relevance of these curves is that the solution Q is going to be constant along these characteristics. This is relevant because these equations, these characteristics, tells us that the solution propagate along these straight lines. So for instance, we might have some Q value here, and yeah, the Q values propagate along these characteristics, and the solution Q is going to be constant for each curve. So some Q is going to be constant along this curve, the green one, another Q might be constant along this one here, and this is the case for when the fluid velocity is greater than 0. When the fluid velocity is smaller than or negative, the direction of the propagation of the solution is going to be from right to left. And in addition, these characteristics are also important because these equations tells us that the solution can be traced back along characteristics. So for instance, let's say we might have some Q value here along this characteristic with these characteristics are straight lines which have a slope of u bar, and then if I have some Q value here, I can trace back along the characteristic. So that means that Q can be found by determining the x0 from which the solution propagated. So yes, this is what I was saying, that if we are sitting here and then if we move along here, this direction, we can find the value x0 from which the solution Q propagated. So with equations, this means that x0, which comes from this equation, can be isolated from here, and then we have this equation, and now we evaluated Q at capital X0 at time equal to 0, and then from here, from this equation, we obtain x0. So Q, the solution, is just evaluated at x0, which is these terms. So Q evaluated at x minus u bar multiplied by t, evaluated at time equal to 0. So that is, this equation is going to be reduced to this right hand side, which is just the equation that we obtained in equation 19. So this is another way to find the solution of this PDE, the linear advection problem. So those are the characteristic curves that are going to be important in explaining some finite volume methods. Another important thing is that the characteristic curves transport information from the initial condition. So as I was saying, so if we impose some x0 here, the Q values are going to be propagated from here to here when u bar is positive. When u bar is negative, the information from that comes with Q is going to be propagated from right to left. So now before, in the exercise that I included here, we impose these conditions that consider that the spatial domain is infinitely long, but that's not the case for real systems. So real systems are actually bounded. So that means that they are defined in a limited interval. So the domain omega is bounded. So that means it has it has a lower limit A and an upper limit B. So this is an example. So we have a geometry that has this cell size, which is B minus A. So So we want to study the behavior of the linear advection equation within these boundaries. So from the characteristics, we know that when u bar, when the fluid velocity is positive, the information will be propagated from left to right as t is being increased. And thus, remember, we are solving a simple PDE. Also remember that in order to solve this PDE, we impose an initial condition, but we also need one boundary condition. So we have not talked about boundary conditions until now. So when you are studying these cases, these bounded cases or limited domain cases, you have to choose where to impose your boundary condition. So physically speaking, it is much more relevant to impose your boundary condition at here, because this is the point, this is the border when information is being propagated when the fluid velocity is positive, because the propagation q is being propagated from left to right. And it does not make sense that you want to impose your boundary condition here in B for this case, because yeah, there might be some information entering here, but it's never going to enter the system, because all the information is coming from left to right. The opposite case is seen when the fluid velocity is negative. Now, from the characteristics, we know that the information is being propagated from right to left. So it makes much more sense to impose your boundary condition at this x equal to b. Yeah, for the same reasons that yeah, information is being propagated in this direction. So it does not make sense to impose the boundary condition on A, because otherwise the information will enter here, but it doesn't make any physical sense, because the information that is entering through A will be ignored, because most relevant information comes from the other side, from the other direction. So with this slide, I conclude this first presentation where I talk about hyperbolic conservation rules. So in the next lecture, I will be focusing on talking about the finite volume methods, which are the most popular methods used to solve this kind of equation. So thank you everyone for watching this. See you in the next video.